Today we're looking at the continuous distribution. It's a different way of looking at CPM, and basically we're trying to answer the question. Say the customer comes to us and says, what are the chances the project will be completed in 20 weeks? We have our activity code. I draw out the really simple diagram. What we were using as our activity time is now what we're calling the most likely scenario. So if I graphed out the times, we find that our critical path was ADE with 19 weeks and DEF had 17 weeks. To that, we've added a best case, worst case scenario. Generally, you do this in business. You'll ask people for when the project will be completed, best case, worst case. Some people call it optimistic and pessimistic. Again, but I usually use best case, worst case. So with this information, we're going to take a weighted average of our 3 times, and we're going to compute our standard deviation, which will allow us to do a continuous distribution. We're going to use the range method for the standard deviation. All right, first thing we do is compute T sub E, which is our weighted average. This is just an example. We have 3 numbers. If we averaged them together, it would all be the same number, a weighted average. We're using different percentages. So we just randomly, in this example, 25% of A, 50% of B, 25% of C. That's our weighted average. We could write that as A plus 2B over C divided by 4. Because remember, 1/4 equals 0.25, 1/2 equals 0.5, and for those of you that love fractions, 1/4 plus 1/4 equals 1/2. So if you go through and do the math, you can find out that these are equivalent. Our averages have to equal 1 or 100%. 1.25, 0.75, 1, so that makes 1 right there. What we use for this calculation for TCC is we're going to use 1/6 of A, and A being our optimistic or our best case, 2/3 of M, which is we've been calling the activity time up to this point, or our most likely, and 1/6 of C, which is our worst case or our pessimistic. This is kind of the standard way to do the weighted average. Just another way again to rate the state's weighted average is A plus 4M plus C divided by 6. And if you go through with the fractions, you find out these two are equivalent. All right, so I just went through and I filled in my T sub E. In this case, we had an optimistic of 7. We had a most likely of 8 and a worst case of 10, and we divide that by 6 because effectively we have 6 pieces here. So that's 8.33, and I just went down A through F likewise in the same manner. All right, next we're going to compute the standard deviation using the range method. Our range is just simply the worst case to the best case. So that's our range, and the 6 comes from there's 6 standard deviations over a normal distributed curve. Kind of the empirical rule, we'll get 99.99%. Remember, in a real project, say like if we were building a new dormitory, there would be 100,000 operations here. So when we combine together all those averages, it would come out pretty well. Just using 6 numbers, again, our sample size is probably a little small here. But anyway, so it's the worst case minus the best case divided by 6. It's typically abbreviated B minus A divided by 6. So I just went through and I did all the calculations. 11 minus 7 divided by 6 is 0.67, and so on down the line. Okay, so notice what this does to the completion time of our path. If we use the T sub E times versus just the most likely times. Our first path, ABC, came out to 19.33, and originally that was 19. So again, our time increased a little bit. You'll see that people tend to be a little bit optimistic about time lengths. D, E, and F now came up to 19.17. This was at 17 weeks, so that's really a dramatic jump right there. So these are our X sub R, or our means. Remember, we took the weighted average, so that gave us an average, which is kind of the definition of the mean, if you will, the X bar. So then next we have to find out the standard deviations of the complete paths. The individual deviations we add them basically as variance, because remember the standard deviation is the square of the variance. So for ABC it comes to 1.01, for DEF 2.19. So now we have enough information that we can answer our customer's question, what are the chances we'll get done in 20 weeks? Okay, finally we can find out our percentages for the customer, which again is basically the area underneath the curve here. From our calculations, we know our X bar. That was our weighted average. So for path A, it's 19.33. Path ABC, it's 19.33. The customer is asking about 20 weeks. So that's our X sub I. Similar for path D, E, and F. Our X bar came out to 19.17. And again, the customer is asking about 20 weeks. We calculated the path standard deviation for ABC at 1.01 and DEF at 2.19. So if we go through, so this would be 20 minus 19.33 divided by our 1.01, which would give us a Z-score of 0.38. Similarly, over here, if we looked at our Z, it would be 19.17 divided by 2.19, and this would give us a Z-score of 0.66. On the Z table, if we went over to 0.3 and up to 0.08, we came down, we would find that this is this is 6480, which is 64.8%. In here with 0.66, we do the same thing. That would give us a 0.7454 or 74.54%. So when we're replying to the customer, remember the question he said, what was the chances are that we would finish up in 20 weeks? Well, we take the lower of these two percentages. So we'd give them a 64.8 or a 65% chance that we could complete the project within 20 weeks.